last time we sort of just did the simple idea about incompleteness of space-times, and we saw that in many times it is just because the coordinates we chose happen to be not good coordinates. The metric itself is perfectly fine, and one way of looking at that was to look at this geodesic completeness of space-time, and that has been a traditional way of looking at the if the space-time is actually there is a real singularity or there is not. And last time there was also a question about whether geodesics refer to particles, and should we not use the field equations themselves for fields. And the point is that yes, we can, but the examples that we have seen and examples we are going to see today, they all have the property that in fact it doesn't really matter, because we just see that the space-time is geodesically incomplete, but that is admits a complete extension which is completely smooth and analytic, and therefore we know that the problem was just a coordinate problem and not a problem with singularity. We know that already, and that's all we need to know right now. If at some stage we actually arrive at a kind of what we think to be a true singularity, and then the question is, can we extend beyond that true singularity, then the issues about the field equations of Einstein's equations in this case will arise, whether the Einstein's equations admit a solution which is with sufficient differentiability across the horizon, across the singularity. So to summarize, the geodesic incompleteness that we have seen was completely sufficient to just tell us that in fact what we saw was coordinate singularity and not a genuine singularity, and so there's no problem. And so we're going to do the same thing today. So the fourth example that we're going to see now this is just the Schwarzschild space-time itself that we talked about. And usually, not always, but usually there is no problem, so to say, in the angular directions. These are heuristic, because I'm not defined for you any chart to talk about angular direction. But heuristically, there is no. Space-time is 4-dimensional. There is a 1-dimensional time, 3-dimensional space, and there is usually no problem in the angular direction. The problem of incompleteness occurs in the RT plane. This is all heuristic, just roughly speaking. And so now, in Schwarzschild space-time, then we can just look at the 2-dimensional metric. This underbar just means I'm not looking at the full space-time metric. I'm just looking at the RT plane, and then that looks like minus 1 minus 2 n more r dt squared plus dr squared upon 1 minus 2 n more r. And what we see here is that apparently there is a singularity at r equal to 2m, and what we are trying to see is if in fact the situation is similar to what we had seen in many examples, the first 3 examples, where it was really a coordinate singularity, space-time admitted, or the metric admitted a completely nice extension. It does that happen. So here, of course, the coordinate range is r is bigger than 2n, and t is going from minus infinity to infinity. And we see here that there is no time dependence in the metric coefficient. Even if I had added the angular part, there is no time dependence there. Therefore, in fact, d by dt is a killing back field. In this chart, d by dt is a killing vector field of the metric, and so that's the reason why it is time-independent metric up here. Then what we want to know is, well, is the problem. So we saw last time that typically in these 2 dimensions, it is easier to just take out the conformal factor, write the metric as explicitly in the conformally flat form, and it's obvious what conformal factor to take out. We just take this out. So I get here minus dt squared plus dr squared upon 1 minus 2 n more r whole square. And so the question is whether, so now it's exactly what we did last time. So this was like the t coordinates, and this was like the z coordinate, and we had 1 upon z squared last time, and we got another factor up here. So what we want to know is that, well, we would like to define dr star to be equal to dr upon 1 minus 2 n more r. This is a total differential equation, and so we can just define a coordinate r star such that this is true. And this just tells us that R star is equal to R, let me get the signs right, plus 2m times log of R by 2m minus 1. So this is a solution of that. And so now we see immediately here that as R goes to 2m, R star goes to minus infinity. And this is really like in the Riddler example that we saw last time. Therefore, R star is like the coordinate zeta. It was also the case that in terms of zeta, the apparent singularity in the metric in the Riddler case was also sent to minus infinity, and that is what is happening up here also. So therefore, this R star is often called, Wheeler called it the tortoise coordinate. This is figurative. Tortoise are the things which walk very slowly. So the idea is that as R goes to 2m, we reach this what we know to be now the horizon. R star is going to minus infinity. So R star is going very, very slowly. That is what was just called tortoise coordinate by Wheeler. It's good to note such these terminologies. And now our idea is very, very simple. I mean, so because now we can write down the metric again. It's exactly like last time, 1 minus 2m over r times minus dt squared plus dr star squared. So I written the metric in a manifestly flat form, and again r star is the coordinate range is minus infinity to infinity because of the log term there. Okay, so that is the tortoise coordinate of the metric. And then now, remember the whole idea was to now just introduce null geodesics. And so, again, this is a confound factor times a flat metric. We know what the null lines of this flat metric are. They are going to be little u is t minus r star, and little v, which is t plus r star. And if I do that, then I do the square just becomes 1 minus 2m over r upon minus du dv. And so this is our metric. So it looks exactly the same as what we did in the Riddler case, where the metric written as of manifestly du dv in null coordinates times some confound factor. The confound factor now is a little bit more complicated than in the Riddler case. The Riddler case it was much simpler, but it is not very. Our job now is to take this confound factor and try to express it as much as possible in terms of u and v. In the Riddler case, we could explicitly write it in terms of u and v without any problem. Now it is a little more complicated, and that is the only complication really in going from the Riddler example to the Schwarzschild example. That this confound factor, which involves r, is a little bit more complicated, and therefore its expression in terms of u and v is a little bit more complicated. And so just a simple algebraic manipulation. So you just use these two facts. So we just use these two facts, namely r star is defined like this. This is the thing that, and then we use the fact that the u and v coordinates are defined by that. And it's just simple algebra. We can just do the algebraic manipulation, and you can check that 1 minus 2m over r is given by 1 minus 2m over r is just given by 2m over r, or a factor, times e to the minus r star upon 4n times e to the minus r upon 4n times e to the r star. So therefore, this r star, I can quickly write what r star is, right? R star is just u and v are just given by this. Therefore, r star is just given by v minus u divided by 2. Sorry, this may be right. Yeah, this is correct. So r star is just given by v minus u divided by 2. And therefore, I can just write down the metric now, ds bar squared, as the conformal factor, which is e to the minus r by 2m. This I leave as it is. This is the conformal factor. This conformal factor up here. Times, for the r star I substitute, so I get here e to the v upon 4m, e to the minus u upon 4m. I'm just substituting up here, times du dv. And now it looks almost like what it was in the case of Rinder spacetime, except that there is a conformal factor sitting out here, and then these, in the Rinder spacetime, it just look exactly like this. E to the v times dv, and e to the minus u times du. So these factors we can just absorb in here by defining new coordinates, if you like, and this new. So this conformal factor, we keep it as it is, and we define new coordinate u to be equal to e to the so du. So e is equal to e to the v upon so u is just given by u is just minus e to the u upon 4m d1, and similarly v. Not the other way around. Sorry. U and v just defined by that thing, and therefore du will be equal to this, and dv equal to v upon 4l. Okay, and therefore we can just substitute. These two minus signs cancel, so I get plus here, and therefore ds bar squared is just given by 2m over r. So I leave this confound factor as it is. I don't do anything to it. Upon 2m times du dv. And the important thing now is the following. First thing, that this factor up here is regular at r equal to 2m. The problem was with r star, right? Because r star became minus infinity at r equal to 2m, but we wrote this r star in terms of v minus u. Even then, if there's a problem, this is still minus infinity. But then the statement is that we redefine the coordinates v and u, and therefore we sort of absorb this bad behavior in the coordinates u and v. In other words, the idea is that little u and little v and r star are bad coordinates, they are not well behaved with the horizon, whereas a capital U and capital V are good coordinates, they are well behaved with the horizon. So we got this, and then as in the Rinder case, u is going from minus infinity to infinity, and v is going from infinity to infinity. So r star is doing this, and therefore u and v are also going from minus infinity to infinity. But because of this exponential factor and a minus sign, u is going from minus infinity to infinity, and v is going from infinity to infinity. So sorry. U is going from minus infinity to 0, and v is going from 0 to infinity. So it is exactly as in the case of the Rinder space-time, that what we find is that in fact, we started with this on space-time, then we wrote it in the conformally, manifestly conformally flat form, then the flat metric we wrote in terms of null coordinates, and then we just manipulated this. So the confound factor is still bad at r equal to 2m, but we manipulated the confound factor so that the bad behavior, if you like, is absorbed in this new coordinate transformation. Up to here there is a bad behavior. Up to here it looks like there is no bad behavior, but there is, because of the fact that u and v becomes they diverge. These coordinates diverge. R star v minus u diverges at the horizon. So therefore, this behavior is not a good behavior. But then we handle it by saying that, well, that was a problem with the coordinates u and v. Let us define new coordinates which we declare to be good coordinates, and they are really capital U and capital V. So this is really very similar to what we did yesterday for the Rindler case, and therefore we can again define the T and V T and R coordinates now. T equal to U plus V, capital V upon 2, and let's suppose R to be equal to V minus V upon 2. So if we define this, then the metric just becomes e to the 2m over r times the conformal factor r by 2m e to the minus r by 2m times times du dv. So that just becomes minus dt squared. So this is manifestly flat form, two-dimensional Minkowski space times the conformal factor. So the difference from Rindler case was that in the Rindler case, this new metric we obtained in these new coordinates, which we now want to declare to be good coordinates, was just flat metric. Now it is not flat, it is still conformally flat, it is the conformal factor. Therefore, this metric is going to be, now we can just extend the space-time. This is the key point. So the two key points were, up to now, we're just doing manipulations. The first key point was defining these coordinates u and v. And then the next key point is now we extend, obviously. We extend space-time so that u now is minus infinity to infinity, v is now minus infinity to infinity. Right? We extend the whole range of these coordinates. And the same thing therefore happens with t and r. So t also is minus infinity. Let me not. So t and r are the same thing because they're just given by u plus v and u minus v. So what is happening here? What is happening is that I got this space-time. Maybe I should write it space-time out here. I got this space-time up here. Now this is r and this is t coordinate. And this is just a flat metric in this coordinate. And this is a conformal factor. So obviously the metric is perfectly fine wherever the conformal factor is good. Now we look at the conformal factor and we see there's no problem at r equal to 2m. At r equal to 2m, this is equal to 1, this is equal to 1, and then I just get this metric, which is in fact as good as it could be, and so there's no problem at all at r equal to 2m. So the first thing is that no problem at r equal to 2m. So this was, therefore we conclude that this was a coordinate singularity. The physical metric is perfectly fine. We just happen to express it in coordinates which go back. That's what is happening up here. And now, what was the original space-time? The original space-time was r bigger than 2m and t minus infinity to infinity. That space-time just trickles down to space-time where u and v have this range. So it's exactly like in Rindler case. So this is u equal to 0, and this is v equal to 0. And then the physical space-time, as exactly as in the case of the Rindler space-time, was just, the original space-time that was given to us was just this coordinate. It was the one when u is negative and v is positive. So it was this coordinate. And what we achieved here is just to extend it completely. So until where can we extend it? Now in the Rindler case, there was no confound factor, and therefore we extend it everywhere. There's no problem. But now we have a problem because there's a confound factor. So we have to know when is this regular, right? So as long as this is regular, the space-time metric is perfectly well defined at all points of t and r going from minus infinity to infinity. But we see that this confound factor is a problem at r equal to 0. Right? This diverges at r equal to 0. So the question is that a real singularity, or is it a singularity of the type of r equal to 0 in the spherical polar coordinates that we saw? That there was a problem at r equal to 0, but there was no real problem because we expressed it in good coordinates and the metric was perfectly fine at r equal to 0 in the spherical coordinate. So is that a problem? Like r equal to 0 is a problem because of that, or is it a regular singularity? Now fortunately what we can do is just simple. We can calculate curvature invariance. Remember what I said last time, that namely to test if there is a singularity, we can always calculate curvature invariance. For Maxwell field, we can just calculate FAB or FAB star FAB. These are invariants, and therefore, if they blow up, then the Maxwell field clearly blows up. Similarly, here we can calculate the curvature invariance. If they blow up, then there is a singularity. But the problem was the other way around, namely, if they don't blow up, then that doesn't mean that there is singularity. Because of the indefinite signature, these invariants can even vanish, or if you like, the singular behavior can be cancelled out between two different terms because of the indefinite signature. So, but now let's just ask, is R equal to 0 or true? That is, it's a curvature singularity. Does the curvature blow up there? Or is it a coordinate singularity? That's what we want to ask. So we can calculate the curvature invariant. It's called Kretschmann scalar. And that is just given by the Riemann tensor square. Again, because of the indefinite metric, this is not necessarily a positive definite quantity in general space-time. So if it is regular, it doesn't tell us anything. It may be that the metric is still bad. This particular quantity happens to be regular. But it turns out that this quantity is equal to, in fact, 48 m squared upon r to the 6th. So the Riemann tensor goes like m upon r cubed. We should put g squared m squared. Sorry. Upon r to the. So I mean, strictly speaking, here it should be 2gm, right? In the metric. Because just for dimensional reason, rc squared even, if you want all the dimensions, rc squared. So I'm putting c equal to 1, but sometimes we'll just restore g just to tell you that where the gravity is important. C is always equal to 1 because we're always talking about at least special relativity. So therefore, the statement is that we see here that this diverges at r equal to 0, and therefore it is in fact a curvature singularity. So the space-time is genuinely incomplete at r equal to 0. So now we want to know where is r equal to 0 thing in this little r equal to 0 here. And that is kind of, just want to emphasize to you, this has been always an issue with Schwarzschild space-time, namely, our good coordinates now are u and v, but the conformal factor requires r. And I have to write r as a function of u and v. Of course I can go back and write it. But as we'll just see, in fact we did it, right? We somewhere here we wrote down 1 minus 2mr in terms of these quantities. These are just little u and little v. This 1 minus 2mr or r was just this quantity up here. And so, so I think I missed a sign here. I'm so sorry about that. I should have a minus sign here. That just carried over from here. This sign was missing before. So we got. So we can do that, but now the question is, let's just do it more carefully and see what happens. So what we know is that r equal to 0 is singularity. And we want to know what is the nature of this singularity. Is r equal to 0 really a point? Is a line? Or what is it? Now, this is an important fact that you should keep in mind, that naively you would think that if I have a point particle, like for example in the Coulomb case, the point particle is just sitting at the origin. Therefore you think that his world line is a time-like line, and therefore singularity is along a time-like line. So naively you would think that, well, this really is very similar, it's really the general relativistic version of a Coulomb particle, and if it is sitting at the origin, and therefore I got this singularity r equal to 0, and r equal to 0 should be in fact a time-like line. This is wrong. And these are the issues that happen, counterintuitive things happen in general relativity, and this is something that you have to just explicitly check what happens and what does not happen. In other words, what is the nature of this r equal to 0 singularity is something that you should not, I mean, it's good to have intuition, but every now and then general relativity comes and corrects your intuition in a rather dramatic way, and this is one example. So what happens after r equal to 2m? So we see here that we just saw previously that 1 minus 2m over r was equal to, so I'm just taking the thing that we had before. So I'm just doing this algebra that we did before, and I'm just short-circuiting, going from little u and little v to capital U and capital V, and you can just check that in fact this equation which gave us what is 1 minus 2m over r just becomes the equation which is r upon 2m minus 1 is equal to e to the minus r upon 2m times u plus v. So therefore the statement is that at r equal to constant lines, if r equal to constant, then this is constant, I can divide if I like. R equal to constant, not equal to 0. Well, it can be even 0, but if r equal to constant, then the statement is that I can just see here that uv is equal to constant. You run through this more carefully, and you can check yourself very quickly that in fact this constant is negative if r is bigger than 2m. So it's a constant value. If this value is bigger than 2m, then it is this constant is bigger than 2m. Sorry. And then it's positive if r naught is so that means that r equal to constant lines, if r is bigger than 2m, r naught is bigger than 2m, then these lines are time line. So u times v is equal to constant, and that is actually going to be negative. So these lines are actually time line. So I'm going a little bit fast, but this is the thing that you can just go and verify by looking at the formula in detail. Don't want to spend too much time on algebra. That when uv is equal to constant, and then if this constant is negative, then you can check that means that the line is actually time line. So in this region, r equal to r naught is actually time line. In this region, when r is less than 2m, this constant is positive, so then you go back and see what happens up here, and you will see that that line is actually space line. So how do you check it is space-like or time-like? Well, you just take 2 points on this line. So this is u and v coordinates. This is going to be u plus delta u, v plus delta v. And you want to just calculate what is the length of this interval just by going and substituting in the metric. Substituting in the metric up here, minus. Sorry, this is a key point. So this was this minus sign trickles down, which I forgot, to this minus sign up here. So just substitute in this metric, u and v, change it by u plus dv if you like, u plus du and v plus dv. Right, you just see, just substitute there, see what is dA squared. Is dA squared negative? If it is negative, then the space is, then this little interval up here is time-like, and you will find it is negative for this part of space-time, and you'll find it is positive for this part of space-time. Okay. Any questions up here? This is going too fast for people who are taking it for credit, who have not seen it before.
I have a question when you extend the capital U and V, because in your definition, the capital V equals to e to something. Is always positive? How do you define to be negative somehow?
No. So, yeah, capital V is always positive.
Yes.
And now what we're saying is that you extend the space-time. That is where the non-trivial thing happened. That's why I put it here. Maybe I should highlight it further. We say that, well, this was our old space-time. And we're trying to see, of course, when capital U and capital V are their boundary, U and V equal to 0 up here, those were the boundaries of this original space-time, where R was greater than 2m. Right? Yeah, but we see that there is no problem with the metric. There's no reason why we should really stop the metric in this region. So the original space-time that was given to us really covered only this part of the manifold. Namely, as you see here, V is positive. V is positive in this side.
But if I have negative V, how do I map back to the real space R?
Alright. So the statement, yeah. So this is the mapping. So we extended. Very good question. So the question is the following. Originally, I had T and R as coordinates. From T and R, I went to U and V. And now I say that extend this. Now on this extended space-time, I would like to say that I should also be able to define what is R and perhaps what is little t, the original space-time coordinate that we had up here. Well, R we just wrote down explicitly. And we see here that there is no problem. I mean, even at R equal to 2m, then you will find that uv is equal to 0, but it's not, doesn't blow up or doesn't, nothing very, yeah, it's equal to 8 just because it is these lines up here. Nothing happens there, R equal to 8. So therefore we can define R here. But your point is well taken. It is conceptually confusing as to say, wait a minute, I had R and T, the metric was bad. I now write U and V, and extend it, the metric is good here. So what happened, to my old coordinates? The old coordinates were not supposed to be good, right? That's why the metric was bad. But on the other hand, I see here that R can be extended completely. But previously the metric was bad at R equal to 2m. So lesson number 2 from general relativity or differential geometry is the following. We intuitively thought that something was wrong with the R coordinate at R equal to 2m. But in fact we see there's nothing wrong with R coordinate at R equal to 2m. Therefore, just logically, even though it seems counterintuitive, something must go wrong to the t coordinate, little t coordinate at R equal to 2m. And indeed that is the case. And I emphasized this last time already in the Rindler case. In the Rindler case also it was the case where I got z and little t. And the metric in the Rindler case, remember, looked like z squared times minus dt squared. Plus, I should write just like that. The metric looked like that in the Rindler space-time. And normally we would have thought, oh, z equal to 0 is a problem, so z is a bad coordinate at z equal to 0. And we saw there, in fact, finally, z is a perfectly fine coordinate at the horizon. What is bad is really the little t coordinate. I leave this as an exercise for you to go back and check that little t coordinate, in fact, is a problem. And now in this case, the statement is that indeed, what is problem is R is a well-defined function, completely well-defined function, coordinate on the entire space-time. I'll put a fill in parenthesis in a second, what I mean by entire space-time, but t goes up. So, our old metric was bad, not because something went wrong with R, but something went wrong with the coordinate t. Okay? So, two things that we learned today, just 1 second, two things that we learned today is that where things go, that's all right. Where things go bad, right? That's the question. And the first thing is that the old coordinates were bad at the horizon. What was bad was that in fact t blows up. And earlier on, we saw another counterintuitive point of view, which is that in fact R equal to constant lines are not necessarily time-like everywhere. Inside the horizon, I'm just calling R equal to 2m horizon right now. Inside the horizon, they are in fact space-like lines. So these were the two counterintuitive things that we saw. Eugene.
Simple question. The metric we started with, we know it's a solution of Einstein equations. Now we are extending this metric via this procedure. Is there some argument guarantees that the extended metric is still a solution of Einstein equations?
Right. So the statement is basically that we know that this is, yes, there is. So the idea is that we know that this is a solution of Einstein's equation in these coordinates. So RAB, the Ritchie tensor, is equal to 0. I just in fact, even if I made a smooth extension, the C2 extension, then see some sufficiently higher extension, then I would not have no. But in this case, we are making an analytical extension, and therefore the statement is R equal to 0, RAB equal to 0 at some region, and therefore it's equal to 0 also in the continuum. So we have an analytical extension. We can make a stronger argument, but let me not get into that, because then I have to put caveats and such things. Okay. Okay, any other question? So again, we have done something very non-trivial, and the non-trivial thing happened at, up to here we're just expressing everything in terms of what look like a good coordinates. The non-trivial thing is extend space-time, and this is what happened. And now what we are saying is that r equal to constant lines inside the horizon are space-like, and outside the horizon are time-like. So in particular, r equal to 0 is some space-like line. And there are two, actually, space-like lines are equal to 0. The whole thing is, as you can check yourself that you can also, when extend the space-time completely, but uv equal to constant will correspond to two lines. This one is going to be a line here. If you specify what that constant is, you will get a line up here, and you will get here r equal to r naught less than. So if you give me a particular value r naught, then the statement is that I actually get two lines in this line to line diagram. Similarly, on this side, r equal to r naught, I'll get two lines. So in many ways, near the horizon, the space-time looks like what the Rindler space-time looked like, right? It's very similar to what we saw last time to be Rindler space-time. Good. And now the only singularity, as we saw, is a curvature singularity at this r equal to 2m, and the important thing is that it is space-like. So this intuitive picture we have is that there is a particle moving along some time-like line, which is a picture which comes from Maxwell theory. In the classical space-time, the charged particle is just sitting here. That means in space-time, world line is just following a straight line up here in space-time. And then the Coulomb field is actually singular along this time-like line. But what we see up here is that, in fact, the field is singular, gravitational field is singular along a space-like line. So you cannot really think of this solution as being the external field of a particle which is following a time-like line. That's just incorrect. So this is some intuition that you have to again correct for yourselves. Okay, so now just a few things that we would like to conclude with. So various remarks up here. But before I make the remark, let me just say that for those who are taking the course for credit, and also for those who are sitting on the course but don't know the material already sufficiently well, the homework assignment is on the web. I've added as many of you as I know on the list on the web, so that you should be able to see this. And this is under announcements. The first announcement was lecture notes. And the second announcement is his homework. The lecture notes say explicitly that this is, this is only a draft and so on. And I already noticed so many typos, so I'm going to go and correct them as much as possible as I go along. But if you have any questions, please ask me. The second administrative thing I want to say is that, well, I would like to have office hours. Since we don't have class on Friday, is Friday a good time? Those who are taking the course for credit especially should tell me. So I was going to propose Friday, but after, so say 11:30 to 12:30. Maybe. Is this a good time for office hours? So Friday. So this is also good because then you can look at the homeworks, and if you have questions, you can come and ask me. The homework is due on not this Monday, but the following night, so in 10 days. So it's on the 22nd. Okay, this is office. All right. Okay, so now let's just make a few remarks, and then we'll conclude. So this thing. We already saw that T diverges. R is smooth, in fact analytic. So we can continue at the R coordinate everywhere. And so T blows up here and T blows up here. But once you are in this region, you can again introduce T. So you can introduce T in this patch, in this patch, in this patch, and in this patch. But on the other hand, it blows up here. It's T equal to infinity here. So you cannot really continue along here. So T is a bad coordinate, is the main point that I want to say. But this is the second fundamental confusion of calculus. Namely, T is a bad coordinate does not mean that d by dt is bad. Right? D by dt is always R equal to constant is d by dt. So I want to say d by dt is smooth. Because integral curves of d by dt are just R equal to constant. At the horizon, which is this null cone, which is what we'll call horizon, this vector field TA, so such that we feel like whose components in the TR original TR coordinates are 1 and 0. So this vector field T that I got in the original chart of TA, that vector field is null on the horizon. So d by dt vector field, this is the integral curve of d by dt vector field. As I said, T becomes infinite up here, but I can forget about that. I don't try to continue T at all. But over here, again I have U and V, and I can try to go back and revert to R and T. And I can successfully do that. And again here, d by dt looks like that. And then here, d by dt will actually look like that. Just because d by dt is smooth, so it is going in this way. So on the horizon, it is going to go like that. Therefore, over here, R equal to constant, it should go like in this orientation should be like that. Therefore, over here, the orientation is like that. So on this horizon, the orientation is like that. Then it is path directed because of just continuity. And then on this horizon, the orientation is going to be like that. And on this horizon, the orientation is going to be like that. Because of here, it just goes like that. So these arrows are important. So here it is in the future directed. Here it is a future directed null. So here it is null. Here it is time-like. Here it is space-like. Then here it is null again. But it's path-directed null. It's path-directed. Here it is null, it is time-like, but path-directed. Here it is again space-like, and here it is null and future-directed. So the Killing vector field has this very interesting structure. It exactly looks like the boost Killing vector field in Minkowski space-time near the horizon. But there's a huge difference, and please keep in mind, because people always think, oh, short-shaped Killing vector field is just like the boost Killing vector field in Minkowski space. No, the reason why it is not is because out at infinity, this Killing vector field d by dt just looks like a time translation. At infinity, where we got our short-shaped coordinates are very good, so at infinity, d by dt or TA, it just looks like a Minkowskian time translation. And that is why we always label the Killing vector field depending on what their behavior is at infinity, and that is why it is called a time translation Killing vector field. But near horizon, PA looks like the boost in the regular spacetime. Two-dimensional Minkowski spacetime. So the killing vector field here is does something non-trivial. In Minkowski spacetime, if you are just in flat spacetime, then the killing vector field is either time translation. So if you are in a flat spacetime, then my Gaussian null cone is like that, and the killing vector field is either time translation, which is it's always future directed. It's just a time translation like that. So that is a time translation killing vector field. And then we also have boost killing vector field. And the boost killing vector field looks like this. Looks exactly like this killing vector field that we are having. Maybe I should use the yellow chalk. Let me see if I can find it. So this boost killing vector field will really look like that. Our time translation killing vector field. Time translation killing field looks like that. And this is the boost killing vector field. So the boost killing vector field is like that, path directed, and then so this is the boost killing vector field. And even at infinity, it is constantly accelerating. Even at infinity, it is constantly accelerating. Whereas the time translation killing field in Minkowski space, so in Schwarzschild space-time, so now I'm going to draw the same diagram, but in a short form. This is Schwarzschild. And here we only have one killing vector field. We don't have time translation and the boost. Here we got time translation, space translation, the boost. Here we just have one killing vector field. And that killing vector field, this is the horizon now. And then the killing vector field that I got up here looks like the time translation killing vector field. Just there's only one, so yellow and orange are the same. And that over here looks like a boost killing vector field. But out at infinity, it just looks like a time translation thing. And this is, so it interpolates between a boost-like behavior in Minkowski spacetime and a time translation-like behavior in Minkowski spacetime. And of course, this is possible because of this curvature. You know, if there was only flatness, then this would not happen. If it was boost, then it is boost everywhere. If it is time translation, it's time translation everywhere. But here we got a curvature, and because of this curvature, there is the interpolation between the two things. Yeah.
If you go to spatial infinity in Minkowski space, doesn't your boost translation also not seem to look like a time translation?
Say it here.
If you go to If you go to spatial infinity over there, right? So like
Yeah. No, it is not. Its acceleration never goes to zero. So its components about the boost killing vector field are always in the t and z coordinates that we used before. So that this vector field is always t d by dz plus z d by dt. Whereas the time translation killing vector field is just d by dt.
Right.
So this vector, this one second. So this vector field, so this one second. So this vector field is always bounded. Its norm is -1 everywhere. This vector field blows up, and in fact, it's not. It is time-like somewhere, then it's going to be space-like somewhere, and so on. Yeah.
Okay.
So even in near space-like infinity, it is actually time-like, but it's not blows up.
Right, so my intuition is failing me because, well, I'm thinking is like, well, t equals 0, I just have ddt in a certain sense.
Yeah,
But that increases by a factor of z, and therefore, okay, yeah.
Exactly. Cool. That's it. Exactly. It increases by factor of z. And of course, if you go slightly away, then you see that this is not at all perpendicular to the t equal to constant surfaces. Okay. Any other questions? Okay. So those who are taking course for credit, and also those who are sort of more junior students, please let me know how it is going. I had to set a pace. I just chose some norm. Maybe this is too fast, maybe this is too slow. Let me know. Also, I have emphasized on the web that in this homework, if the terminology is not familiar with you and to you, and therefore you don't know what it means and how to solve it or something, please come and see me.